Hi, Assalamualaikum, and a very good day to the panel and all the viewers. My name is Ahmad Safwan bin Romali, student in School of Mechanical Engineering from UiTM Shah Alam. Today, I would like to present my final year project proposal. First of all, I would like to portray my special appreciation to my supervisor, Dr. Muhammad Rozi bin Maknawi, for always helping me in order to finish this proposal. My title for the project is Simulation Study on Aerodynamics Performance of Sedan Car attached with Vortex Generator. Let's begin with this section. I will give some introduction to my project. Aerodynamics of vehicle has been investigated since 1920 and 1930. One of the types of vehicles is a car. When we talk about a car, the external force around it plays the main role to determine its efficiency. The element that is related to achieve the great efficiency includes aerodynamics performance. So, what is aerodynamics performance? In the next slide, we shall look further into it. However, the main point here is that the aerodynamics performance is able to control the efficiency of a car. So, we recall back the first keyword from previous slide, which is aerodynamics. What is aerodynamics? Aerodynamics is the combination of two words. First, aero, and the second one is dynamics. For simple understanding, aero stands for the element of fluid that is being studied, which is air, and the dynamics means the study of an object while moving into that fluid. Aerodynamics performance is the analysis of air motion when it interacts with the moving car. What elements increase the quality of aerodynamics? The elements include the drag force, lift force, and roll moment that can improve the efficiency of car. For this project, the element of drag force is chosen to be studied. Drag coefficient is derived from the drag force itself. From the previous explanation, how we could actually measure the drag coefficient? There is a few options available in this study field. One of them is the passive flow control method, where it uses a vortex generator to trip the airflow before it leaves the back of a car. Literature review is done to retrieve the information regarding to this project. For example, the finding and the simulation process of the article as shown here. This is the objective of the project. The first one is to do simulation and compare the result of drag coefficient between present study and the car manufacturer database. Next, to determine the drag coefficient of various car velocities with vortex generator at different dimensions and fin numbers. The last one is to analyze the pressure contour and velocity field around the vortex generator and determination of critical dimension and fin number with optimum result to drag coefficient. This is the scope and limitation for the project. The simulation on surface area of two different dimensions of vortex generator is done by using ANSYS software version 2020R2. The second one is the analysis of the pressure and velocity on the VG is limited only at the top roof and near the rear car window. And the last one, the simulation is done by using Spalart-Almaraz turbulence model. The methodology of this project is initially start with 3D modeling. The car is modeled with vortex generator based on this parameter. When the modeling process is done, we proceed with the simulation process. We use ANSYS Fluent software to do the simulation process. In ANSYS Fluent software, it has a workbench to configure the modification and simulation on the model. This is how the workbench looks like. It got geometry section, mesh section, setup and solution section, and the final section is result. So, in the geometry section, we import the 3D model from CATIA into ANSYS Fluent to proceed with the mesh section. After we import the car model into the workbench of ANSYS Fluent, we must give a defined mesh to the whole body of the car model because the aerodynamic flows around the whole body. When the meshing of a model is done, we proceed with the next step, which is the solution setup. This is how the setup looks like in ANSYS Fluent Workbench. It has a lot of setup configuration, such as general, models, materials, and so on. We have to insert the correct information into the correct element. We start with the first one, general. We choose pressure-based type for the solver since the project relates with the pressure of air. The next one, we choose absolute for the velocity formulation. And the last one, we choose steady for the time solver. We proceed with the next setup configuration, which is model. For model setup configuration, we focus here. Here is for the turbulence model used in the simulation. As we discussed before, the project used Spalak-Almaraz for the turbulence model. So we have to choose Spalak-Almaraz here. The type of flow is viscous MVC. Now, we proceed with the next setup for material. We have to choose the right component for each material. For example, fluid, we have to choose air, and solid, we have to choose aluminium. Next, we go to the cell zone condition. Here, I will explain in the next slide. We go first into the boundary condition setup configuration. For this project, we have 4 boundary conditions, which is inlet, internal, outlet, and wall. For the inlet element, we have to choose the right parameter, which is velocity. In this project, we have 2 values for the velocity. The first one is 100 km per hour and the second one is 120 km per hour. We have to focus also at the outlet. Make sure the pressure at the outlet must be 0 Pascal. For the cell zone condition setup, make sure the zone name is correct, which is the fluid, and the material also is correct, which is air, to avoid confusion in the next setup for reference value. This is reference value. Reference value is the final setup for this section before we proceed with the solution in the next section. So, this is a task page for the reference value. Here, we have to focus on the area. This area is the area that directly impacts the flow. Also, not to forget the length. So, both of these elements, how we can measure? We can refer the enclosure we made in the geometry section before. It should be noted also that the reference value is computed from the inlet and the reference zone is the fluid. We proceed with the next section for the simulation, which is the solution. In this solution section, we also have to set the right configuration for each element. For example, here, method, we have to choose the pressure velocity coupling to be set as the couple scheme. The green Gauss node is chosen for the gradient. We have to enable pseudo transient for the formulation. So, for the case of report definition, we have to choose or create the right parameter. Regarding to the project, we need to analyze the drag coefficient. So, we have to create the drag coefficient as the report definition. It should be noted that the important part is the surface zone. We have to choose the right surface zone, which is the car. So this is the final step for the solution section, which is the solution calculation. Before we proceed with the calculation, we have to initialize the calculation first with hybrid setting to know whether the calculation would be converged or not at the end of the calculation. The number of iterations is predicted based on where the solution would be converged. Also, the definition of the conversion can be monitored in the monitor section. After all of these steps, we can proceed with running the calculation to get the result. There is three results that can be analyzed from the simulation. The first one is the simulation validation of drag coefficient. So, from the simulation, the drag coefficient for the car model without VG is 0.27622. This means the different percentage of drag coefficient between the database value is 3.8%. The second one is the pressure contour. Just what we can see here, the car model with WG has quite high pressure around the rear end of the roof when it's compared to the car model attached with 3 Vortex generator. The third result that can be analyzed from the simulation is the velocity field. As we can see here, the car model with WG has a quite high velocity field compared to the car model attached with 3 Vortex generator. For the overall result analysis, the simulation will be done for a few more designs based on every parameter as shown here. The drag coefficients are then compared to find the optimum design for the vortex generator. Also, the pressure contour and velocity field will be analyzed to find the different relationship between the vortex generator. That's all for this time. I hope my explanation will be understood very well. Thank you for watching.